Well, now that we know what parametric curves are, we should apply calculus to them. So here is a parametric curve with x equals f of t, y is g of t. They're both functions of the parameter t. That's sort of moving along this way. So it would be nice to be able to figure out an equation for tangent lines to this, or at least places where it looks like a function. So over here it's sort of bad because there's a vertical tangent, and so we wouldn't expect to have a nice formula there. But places like this where it looks like a function, there should be no problem. So if we just pretend that y is some function of x, we see that g of t equals f of t. So the derivative with respect to t is going to be the derivative of f with respect to its variable, which is x, times f prime of t. So what this says, y as a function of x right here, the slope of the tangent line, somewhere like this, is just g prime of t over f prime of t. Another way to write this is this way. And this looks pretty nice because it sort of looks like we're just canceling the dt, even though that's not actually true. For example, suppose x is t e to the t and y is t plus e to the t. The formula tells us dy dx is going to be the derivative of this with respect to t divided by the derivative of this with respect to t, which we get t e to the t plus e to the t. So I have this, and this gives the slope of the curve as a function of t. And notice when t equals -1, the slope is infinite, and that corresponds to a vertical tangent. Here's another example. We want to find an equation of the tangent line to the curve parametrized by these two equations when t equals 3. So let's first of all see what point that corresponds to. When t is 3, we get 9 times 2 is 18 plus 1, so 19. When t is 3, we have 27 over 3 is 9, minus 3 gives us 6. So that's the point on the line. Now we need to figure out the slope. And using this formula here, we have y prime is t squared minus 1, and x prime, here I'm taking derivatives with respect to t, is 4t. So we have t squared minus 1 over 4t, and t equals 3, what do we get? We get 9 minus 1, or 8, over 12. So the slope is 2 over 3. So we can use point slope form to find the equation of the tangent line. We have y minus 6 equals 2/3 x minus 19. Alright, here's yet another example. We're going to find an equation of the tangent line to this parametric curve in two different ways. So the first way, we're just going to use our new formula. So we have dy d theta is secant theta tangent theta, and dx d theta is secant squared theta. Let's see what value of theta corresponds to the point 1 square root of 2. If you think about it, we're really looking at theta equals pi over 4. So the slope at that point we can just compute here. I guess we don't need to because we have secant and tangent written right there. So let's see. At the point we're interested in, secant theta is the square root of 2, tangent theta is just 1, and secant squared is the square root of 2 squared. So we get square root of 2 over 2 as our slope at that point. And so an equation for the line will just be y minus square root of 2 equals this. Now let's try to find the same equation a different way. First we're going to eliminate the parameter. So by that I mean we have tangent and secant, and we know a nice formula relating those two, namely 1 plus tangent squared theta equals secant squared. So in this case that says 1 plus x squared equals y squared. So we're looking at a positive y value, so it's safe to say that y is 1 plus y is the square root of 1 plus x squared. So to find the slope at this point, I just compute like normal. I have to use the power rule. And get this. At the point I'm looking at, what do I get? Well, these 2's cancel. I get 1 plus 1 and 1 on the top, so I get 1 over square root of 2, which is the same thing as root 2 over 2. So we have the slope, and we already know the point, so we get the same line.